Hey, what's up, Physics 30s? Back with Unit 3, Lesson 3, where we're actually starting to talk about magnetism. This is one of the coolest sections, I think. Be a little bit cooler if we were in class and I could actually show you some things, but we'll do the best that we can. What might help you is if you actually had some magnets that you can mess around with as you're going through. So at least two, so you can kind of feel the magnets and feel what they're doing. If you have a compass, that's even better. Not sure if you do. Again, we'll do the best that we can with what we've got to make sure that we are good to go. So, unconnect the keyboard there. And yeah, we'll jump into the whole idea of magnetism. So, things you already know about magnets. They have two poles. They have a north pole and they have a south pole. In other words, they are a dipole. Scientists have never, ever discovered a magnet that is a monopole, so just a north all by itself or just a south all by itself. They're always together in one magnet. Red typically represents north, blue typically represents south, and yeah, things that you've known before. I'm sure you've seen this too, and if you have the magnets that you can play with, make sure you check it out a little bit. Same as electricity, opposites attract and like things repel, except in this case, rather than dealing with positives and negatives, we are dealing with norths and souths. And please don't, like, you're going to see a lot of similarities between this unit and the last unit, the electricity unit. Please keep in mind that like you cannot say that north is a positive. It is not. Lots of people make that mistake right off the bat. Anyways, opposites attract, like things repel. Fairly straightforward stuff there. So just thinking about that for a second here, and I'm sure you've seen toys like this before. I've got one in the classroom. If we ever get back to class, we'll have a look at this there. But anyways, if you have a suspended magnet, that's a magnet that is suspended or hanging there in air, could we predict what those poles on that magnet would need to be? So it looks like on the bottom here, we know what the poles of that magnet are, and knowing that like repels and opposites attract, we could probably say, oh, well, it's got to be like poles that are right next to each other, so a south on top of a south, and a north on top of a north. That would create a magnetic force that would repel the top magnet. Just kind of back into the physics stuff a little bit here. If it is indeed suspended, what physics principle would we be using according to our data sheet? So suspended, we know that that is physics principle 0. And if I wanted to make a force or a free body diagram of that, the two forces that are acting on that top magnet would be the force of gravity pulling it downwards, and I would need an equal but opposite magnetic force, which we'll call Fm, pushing it upwards. Perfect. So nothing really too new there. Just review some things that we've talked about before. Something that is brand new to us is talking about our magnetic field. So magnetic field, whenever we see that, the symbol for magnetic field is B, and because we've got two states, I guess, that a magnet, or two, what's the word I'm looking for? Well, we've got two separate poles, is what I'll use, I suppose, so a north and a south pole. We have to be very, very particular. So when we're talking about our magnetic field, it's the direction that a north pole of a compass would point, or if I skip forward a little bit, it's also if we had a north test particle. Now remember, there's no such thing as a north test particle. Scientists have never found just a north by itself. It's always there. But we could say to ourselves, which way does a north want to go, or where would a north go? I kind of like the compass that we've got here. So which way would the north pole of a compass be? Now we need one little piece of information for this. One convention that we'll be using throughout is if I wanted to draw a compass, it's a circle with a little diamond in it, and the shaded side of the diamond is always going to be our north. The unshaded side obviously then would be our south. So please make sure you get used to that. Please be good to go. Do you know what a compass is, by the way? Compass is just a little tiny magnet that's free to rotate. I think I got that in here in the next slide or two somewhere. Anyways, we need to do, for Physics 30, we need to be able to recognize the magnetic field in 3 different situations. Around a bar magnet, between 2 like poles, and between 2 opposite poles. So, around a bar magnet, essentially goes from north to south. It's closed loops is another thing. Closed loops, another thing that we should know, but always from north to south, because remember, the whole magnetic field is which way a north would go. A north would go away from north poles and towards the south pole. So fairly straightforward around a bar magnet. Between 2 like poles, in this particular case, the 2 like poles are, let's get a different color here, maybe that one, are 2 north poles. So we know that it wants to go away from north in both cases, so we'd have the arrows pointing away. This looks fairly familiar. This almost looks as if it's 2 positives. Again, it's not 2 positives from last unit. And then any guesses what the magnetic field right in the middle would be? If you guess 0, you are spot on. They're canceling each other out perfectly. If I had 2 like poles, so a north and a south, again, away from north and towards south. So make sure you're familiar with these particular diagrams. Make sure you know what's going on. Always away from north and towards south. So you might want to put the video on pause for a second here, because I think you've got these ones in your workbook. Let's see, this is page 107. Oops, 107. Again, put it on pause. I'll do the same here, and see what you can get for these particular questions. So for part A, determine the direction of the magnetic field and the compass around this. So the circles tell you where to draw your compass. Compass here, compass here, compass here. And then for part B, the net magnetic field at point P, draw a vector sum diagram that would represent that net magnetic field at point B. So again, put it on pause, check it out, and we'll get back together and figure it out in a second. All right, so the first one is, remember, it's the direction that a north would want to go, or the direction that the compass would point, and we know that north wants to get away from north. So on the side of the compass where we've got a north pole, this might be harder to draw than anticipated, but that's okay. We would have the north pole of a compass pointed directly away from it. South side would be fairly straightforward as well, as long as I can draw it okay. There we go. The north pole of a compass would be directly towards the south pole of the magnet. Or in other words, we could even add this in a little bit here. My magnetic field directly towards the south and directly away from the north. The part that's a little bit trickier is this one that's on the bottom here. So on the bottom, lots of people might have it at like a weird angle coming away like this, or even coming towards this, and you're absolutely right. Like the magnetic field from the North Pole would be directly away from the North Pole, and the magnetic field corresponding to the South Pole would be directly towards the south. This is getting a little bit messy, so I want to erase it. But if we've got one that's coming away this way and one that's going towards the south this way, when we add those together, it is just directly towards the side. So the magnetic field would be straight this way, and if I wanted to draw the compass would be straight completely. I'm going to draw this compass off a little bit, but straight completely off to the side there. And again, that's because we've got these closed loops that go away from the north and towards the south. Perfect, so it should be straight towards the side. That's a terrible drawing that I just did, but hopefully you get the idea. For the second part of this, determine the vector sum diagram for point P. So for point P, we could pretend that there's a north there, and a north would want to go towards a south, would want to go towards a south, and would want to go away from a north. So if I wanted to add those up in a vector sum diagram, all we need to do is add them tip to tail. So I've got two of them going towards the left, one from the north on this side, one from the south pole on that side, and one of them that is going upwards. That's from the south pole up top here. And then my overall, my overall net magnetic field, the net, would be going up at an angle, so up and to the left. So not so bad, really not so bad. One thing to look at with this, and this is a pretty common test question that we've got here, is Earth's magnetic field. So we know that we've got our geographical North Pole at the North Pole, where you might think Santa lives, our geographical South Pole, where all the penguins live, down at the south there, and you can definitely see, like, here's South America, here's North America, here's us. If you can see that felt pen, there's us right there. And again, this comes to, on our page, we typically say this way is north, this way is south, and humans have been saying that for a long, long, long time. Issue that we see here, though, is if I hold a compass off to the side, so I hold the compass right here, the North Pole of the compass, let me just erase that, try and make it a little bit neater. Oh yeah, a lot neater. Which way would the North Pole of a compass point? It would point towards our geographic north, which means the magnetic field lines would be going in a direction that looks kind of like that, which means that our geographic North Pole would need to be our magnetic South Pole, and vice versa, which is kind of weird. Now you can think about this. Like, if we called this geographic north for a very, very, very long time, and then we discovered these magic rocks, by we, I mean humans in general, we discovered these magic rocks that always point in one direction, the part of the magic rock that always points towards our geographic North Pole, we'd probably call that north. The point that points away from it, we might call that south, because it always points towards south. But then once we later started to understand that our magnetic, how magnets work, we might understand that our geographic North Pole is actually our magnetic South Pole. Again, that's just something that we really need to know. So again, this probably comes from a bit of history here, where we said that the North Pole of the Earth is up here, South Pole of the Earth is down there, and then we find something that always points towards the north. Let's call that north. So just keep in mind that our geographic north is our magnetic south and vice versa. So yeah, back to this. The way that compasses are actually working is to picture a magnet that's allowed to float or allowed to rotate freely. It's always going to rotate so that it is aligned with Earth's magnetic field. Now, one thing to note is that our Earth's magnetic field is actually constantly changing, and it is not perfectly aligned. So our geographic north, that's where we rotate around, is not always perfectly aligned with our magnetic south, but it's usually fairly close, right, to give us a pretty good idea. So, next thing to kind of look at here, and you can check this out as well. If you head over to PhET and search the magnetism app, I've got it going right here. You might need to download Java for this one, but our magnetism app, I've got the compass here, so the North Pole of the compass is colored red, as usual, and then I've got a magnet where I've got the North and South Pole of a magnet. If I kind of trace this around, you'll notice that the North Pole of my compass always, no matter where I put it, points at the South Pole of the magnet, and then the south part of my compass, which is the white part, will always try and point towards the North Pole. If we actually show the field, we can start to see those closed loops again, right? So we can trace all these around. It's like a bunch of little freeze frames for this magnet. If I put it anywhere on there, the magnet perfectly matches the field that we've got right here. So again, closed loops that are going away from north and towards south, which is kind of, if I replace this with planet Earth, you can kind of see in the background, I've got my geographic north with my magnetic south and vice versa. And then we can see and this is exactly why we'd have that, anywhere on the surface of the Earth, the North Pole of the compass would point towards the North Pole of the Earth, which again is our magnetic south. So pretty much any way, pretty much any way we look at that. Now, let's get rid of that. Let's get rid of that. Next little piece to look at is what's actually inside of this magnet, and this kind of gets us into a bit of domain theory, which I'm going to get you to watch a video for in a second. But what's inside of the magnet? Well, when we click on it, it's essentially a whole bunch of little tiny magnets, right? So remembering that this compass is a little tiny magnet, and this is how it's drawn. Inside of a magnet is a whole bunch of little tiny magnets. Those little tiny magnets are called domains. When those domains are all lined up nice and neat like this, we've got an overall magnetic field that adds on itself. If they're scattered, we don't have that so much. So that's what we're going to explore for the next little bit here. So let's get this one going again. Excellent. Oh, and this is the video. So this is where I'll get you to put it on pause and check out this video. 6 minutes and 26 seconds, assuming that there's no ads. Veritasium and Minute Physics are the ones that have put it on. So you could either go through and click on this link, or you could just search in YouTube Minute Physics Magnet. It is the first thing that shows up. It is this one, and it is from people who can do a lot better of a job creating videos than I can. So go ahead and put that on pause now, and then we'll recap and we'll check out a little bit of domain theory. All right, so domain theory, kind of interesting, right? When you watch the video, we've got all these different things. It all comes down to that like electricity connection. It's all about the electrons, and each electron has its magnetic field, but then you see the electrons can cancel out other electrons' magnetic fields, and it's really only things around the edges of the major blocks of the periodic table. Then there's really, when it comes down to it, there's only 4 things that we say are truly ferromagnetic on our periodic table, and these are things that you should know. If you see this, you could see this on unit tests or on diplomas: iron, nickel, cobalt, and gadolinium. The 4 things on the periodic table that are truly ferromagnetic. So make sure you're familiar with those. Make sure you know those. So can't really show you demos, but excuse me. When we talk about unmagnetized materials and metals getting attracted to a magnet, ordinarily we see things like paper clips, coins, stuff like that. They're not really magnetic. They won't stick to each other, but as soon as they're brought near a magnet, they all of a sudden become magnets themselves. So one paper clip can attract another paper clip, can attract another paper clip, and then you've got this huge mess of paper clips in there. So let's have a look at how that works. So the domains, if I have a ferromagnetic material that is non-magnetized, it's composed of a whole bunch of little tiny magnets. We are not going to draw a whole bunch of little tiny magnets with individual norths and souths like you see in this top diagram here. Realistically, what we do is we draw a whole bunch of little tiny magnets like this in the bottom diagram, where the North Pole, the actual North Pole of this magnet, is the arrowhead and the south is the tail. So if it's a magnetic material that is non-magnetized, we see that it's totally scrambled like you see at top here. So the magnetic field from one cancels out the magnetic fields from all the others, and overall our magnetic field is equal to 0 when it's scrambled like that. Right? So again, when the domains are random, when they're all scrambled, the net magnetic field is equal to 0, and none of these paper clips then would be overall magnetic. But if we were to put this in the presence of another strong magnet, so something with a really big magnetic field, what we see is that the magnetic field from the one magnet, this one that we've got on the left-hand side here, can actually influence and change the direction. It can induce, those domains to change and align themselves with the magnetic field. So remembering that each one of those little arrows is a little tiny magnet with a very particular north and south side, and the magnetic field is the direction that a north pole of a magnet would want to go, they're going to align themselves, again, with that magnetic field. So the magnetic field in any particular point is going here, and the domains align with it. Perfect. So we're essentially inducing the opposite pole. So if I were to look at on this right-hand piece of magnetic material now, I've got all the tails going this way. That would be an overall south, and that would be an overall north. And then you could see if this was a paper clip or something, why it would be attracted to the magnet on the left-hand side. Very good. So there are two types of ferromagnetic materials that you need to know about now that we've got an idea of these domains. There are soft ferromagnetic materials like pure iron, and there are hard ferromagnetic materials like alloys. Now when you think about pure iron, it's not really that soft. So it's not like the hardness that we're talking about in terms of Mohs scale. What we're really talking about is how hard it is to change those domains. Right? So a soft ferromagnetic material, it's really, really, really easy to flip around and change those domains. So its natural state might be totally random like we see right here, but then even in a small external magnetic field, we can align all of the domains in the soft ferromagnetic material. So again, big key is all of the domains align easily. And then because all of those domains align easily, it's really easy to create a strong magnet that way. So it creates a magnet on its own. If the magnet is removed, so the original magnet is removed, it's no longer there, typically we see the soft ferromagnetic materials going back to their natural state very, very quickly, so their demagnetized state very quickly. So turn them on, turn them off very quick. Which is one of the big advantages, right? So they can become very strong magnets, and they are excellent temporary magnets. So in applications where you need to turn a magnet on very quickly and off very quickly, these are excellent. One example of this is all of our fire doors at the school. So you'll notice that there's a little magnet, and then on the wall off to the side, this is going to be a terrible drawing. On the wall off to the side, there's another magnet. When we open our doors at the school, so when we swing that open, those two things come together, but as soon as the fire alarm comes off, one of them is no longer a magnet, so it's actually an electromagnet that we'll talk about later. One of them, the electricity stops passing through it, the soft ferromagnetic core is no longer a magnetic material, and then the fire door swings closed and everybody stays safe. Okay, hard ferromagnetic materials, on the other hand, are typically alloys, well, same sort of thing. We can have them unmagnetized, it would look exactly the same. The big difference is that it now needs a much, much, much bigger magnetic field to cause those random domains to be aligned. So a weak or a small magnetic field is no longer big enough. What we need is a really, really, really big magnetic field, and then most of those domains will align with the magnetic field. Again, if they are aligning, we can actually create a fairly strong magnet with a true north and a true south pole. Once we remove that big magnet, because the whole idea of hard ferromagnetic materials, it's difficult to flip those domains, they're actually going to stay like that quite a bit longer. So it's almost like they're locked into place. So even if we get rid of this magnet over here, the domains will still be lined up, and we'd end up with a magnet that's going to last a little while. So these make excellent long-term magnets. So if you have a device that requires a constant magnet, this is the one that you want. You want a hard ferromagnetic material. So I think the last thing that we really got from this lesson is explain using domain theory why a magnet sticks to a fridge door. So fridge doors, things that we want to talk about, is it, so the door, I guess we'll do it this way, is it soft or is it a hard ferromagnetic material? It is indeed a soft ferromagnetic material because it's not a magnet when it starts, but as soon as we put this fridge magnet next to it, then all of a sudden the domains are going to align and go from there. So soft versus hard. So no magnet, domains are random. So in the fridge door, if there's no magnet close to it, the domains are random. But then when the magnet gets close, the domains align and we end up with a attraction. So we could probably even draw that. So places that are not close to the magnet, let's just draw domains kind of being all over the place, scattered, canceling each other out. But as soon as that magnet gets a lot closer, let's see, this is the south side of the magnet that's coming, which means the domains are going to align themselves with the magnetic field, so that the North Pole, and remember each of these little arrows, the North Pole is the arrowhead, the South Pole is the tail, are going to be all over, all of the norths are going to be pointing towards the south, and then the further away you get, the more kind of random it's going to be. But all of these domains, let's switch colors here, domains align, and then we'd end up with, switch colors back, this being overall north side of the fridge, this being an overall south side of the fridge, and we would have an attractive magnetic force coming in. So I hope you can understand. This is a little bit messy here. I'm still getting used to this tablet, but hopefully this makes sense for people. So again, the domains align. Anyways, that is it for Unit 3, Lesson 3. Make sure you're doing some practice on, let me go back there because I don't think I can write on that one. Some practice on page 109 to 110. And we will see you again soon. Bye for now, Physics 30s.